In our previous video, we talked about a free running counter, which basically runs through a sequence of numbers. And today we are going to add more features, add more control to this counter, and design a 4-bit counter which goes according to this functional table. As you can see, you have synchronous, clear, load, enable, and with all those we can see that clear has priority, and then load, and then enable. And we can see that when we have like for example the enable, when it's 1, then we're going to have our current state of the register incremented. So we're going to try and we're going to draw our RTL diagram here, and as you can see, I've already started, and we can see that these are the inputs that we have. So we have the adder, and we also have the zeros, and we also have the input, which is going to be the D. And so we're just going to utilize max right here. And first of all, we're going to ignore the current state of the register, and we're going to connect our max to we're going to connect our next state of the register to our max. And for the initial, as you can see, we have clear, synchronous clear taking priority, and so we're going to connect our 0 to we're going to connect our constant 0 to the input, to the 1 input of the first max. And then we can see that load is going to take the next priority, and so we're going to connect the next max to the input of 0 of our current max, and then we're going to connect that. This is going to be our load, and we say that if we have our load equals to 1, then we're going to have be able to load our to load our register. So this is our load, and so we will connect our load to the input of that particular max when it's 1, and then we're going to say that this is our enable, and we're going to add our incrementer, which is an adder plus 1 to the input when it's 1, and then we're going to connect our next state register, which is our register, to our incrementer. And so when enable is 0, we also can see that when everything is 0 0 0, we will not change the state of our register, rather we're going to have the same state without anything. So this is how our circuit is supposed to look like, and we are going to program this and see how it's going to work. So now let's start programming this particular circuit in VHDL, and we're going to start by making our .vht file, which we are going to name it as a featured binary counter.vht, and we are going to start by declaring the libraries that we'll be using, which is a IEEE library, and we are going to use a std.logic.all, and then also the numeric std. And now we are going to write our entity, and we will also in the entity we'll be writing our ports. We will declare our ports in our entity, and then we are going to write our architecture next. And we are just basically right now making the skeleton of our design. And so in each of our design, we are going to basically subdivide it into 3 parts, and this is mostly what you're going to get in any VHDL circuit that you're going to design. You're going to have the register part, the next state logic, and the output logic. So now let's define our inputs. We have our clock and our register, and the synchronous clear, as we can see there, We also have the load and the enable, and all of them are STD logic 1 bit. And then D is going to be our input, which is going to be an STD logic vector in this case. And we are going to have that from, it's going to be 3 down to 0 at the moment, which is because it's a 4-bit it's a 4-bit featured binary counter. So we also have Q, which is going to be our output, and it's an STD logic vector 3 down to 0. And now let's declare the internal signals, which we have the register, R register and R next, and they are unsigned because we are going to do some arithmetics with them, and these are internal signals. And we're going to write now the process for our registers, which is with a sensitivity list of clock and reset. And for this, we are designing our counter with a synchronous clear. However, let's have our reset to be asynchronous. In this case, it means that we don't have to wait for the clock in order to reset our circuit. And so we say that our R register is going to be 0 when we have our reset. And then we are going to define our clock now. With the rising edge of our clock, we are going to pass on our R next to our R register. So now we end our process and we are done with our register logic. Now we go to the next state logic, where now we're designing our R next, the interaction of our next state register. And we say that it's equal to 0 when we have synchronous clear, when it's equal to 1. So as we look at our table on the left, and else we are going to have unsigned plus 1 when we have load plus 1, when we have load equals to 1. Else we are going to have our R register plus 1. Yes, so we had an error there. We're going to have our R register plus 1 when enable equals to 1. And we are going to keep the state of our register the way when we have anything else. So now we define our output logic, where we round it up with STD logic vector, and we are simply taking our output, our R register, to our output. So now we are done. We're going to create our project in Vivado, and you just open Vivado and basically follow the GUI. We are not going to take any particular part. We're just going to take the default one, and we're gonna let this run, updating. And then so we will need to have our test bench. Now we are going to make our test bench, and we're going to name our test bench as TB. I usually like to start with TB and the name of our unit under test, because it's easy to find it when you are dealing with the large files. And we're going to declare our entity. Obviously here is going to be empty, and inside our architecture we're going to have our simulation. And so that is the skeleton of we just made a skeleton of our test bench. And now we're going to write again the stimulus process. And first we're going to declare our signals, and this is what I like about programming in VS Code. It allows you to really be able to edit your code and interact with your code very easily. And For example, I like to put all my signals in like one after the other sequentially, because I'm able to basically edit very well using VS Code. And so I'll just write for each signal to have each on its own line, because this allows me to edit everything very easily, and also I will not be able to confuse any signal. So I'll just clean my code here a little bit, and now you can see it's very easy to see everything. And we're going to also have one more signal which will allow us to know and to terminate our test bench, and we are going to have this as a boolean, and for the first time we're going to have it as a false. And we will also have the clock period, the clock period in this case, and we are going to have this equals to 10 nanoseconds. So now we are going to write our unit under test, and you will see that this is where we are going to for example, this is where VS Code comes in quite handy. For example, when you want to copy all the signals, you can simply copy it like this, and it allows you to edit multiple lines at the same time if you are having the same same thing to, for example, paste or to write. And so now we're going to write the clock, and we will have, and this is how we write the clock. We let the clock run in our TB, and we also incorporate our done signal, so that when this particular signal is when we say done is when we say that done signal is equals to false, then we are able to stop our test bench. So now let's add a few. We're just changing here the reset to be equals to 0. When reset is equals to 0, we reset our circuit, and we are going to start by resetting our circuit, and then we are going to go to reset equals to 1, and let's just observe and see how we can play around with our signals to be able to observe if the circuit is working or not. So we can see, let's have a synchronous clear equals to 1, and also let's have load equals to 1, so that we can see if we will be able, if our synchronous clear is actually working as expected. And we're going to wait for 3 clock period, and we just put our input to be equals to 2. And now let's have our synchronous clear to be equals to 0, and let's leave our load as 1. And we also will be waiting for the 3 clock periods as well. And in our other input, let's have our load now equals to 0, and let's have our enable equal to 1, and so that we'll be able to see if we will be able to increment our input, or actually input to have our input in the circuit itself. And so in our next input, we are going to have our enable as equals to 0, and in this case everything now is 0 0 0, and we will observe if we'll be able to retain the state of our circuit. So now let's add our test bench to our circuit, and let's see. So it looks like we have an error, and we will just we'll try to investigate here. And it looks like the error is here where we're importing where we're declaring our unit under test. And yes, so we need to declare it like this. So we just save this now, and hopefully there will be no more errors at this point, and it looks like it's okay. So because our clock period is 10 nanoseconds, we just need to change it here so that our initial period for Vivado is also 10 nanosecond. It's usually 1000 nanosecond. So now we can see that our circuit is running, and it looks like there is still an error because the circuit is running but is not stopping. So where is the problem? Where is the problem? Let's see. Let's just zoom in and see why it is not stopping. So it looks like it's running and our output is changing, but oh yes, okay, so we need to make this done simulation true so that the clock will stop running when the simulation is done. So let's reset this and rerun our circuit again, and voila, so it is working now. So let's try to investigate the functionality and actually see if it is working as expected. So well, it's not going to be easy to incorporate that figure. However, let's just look at our figure right now. We have, this is our output and this is what we would like to actually observe. And we'll see that, for example, we have our asynchronous clear here and it is 1, and we can see that everything is 0 0 at this point. And let's just change our input. We can see that our input is 0 0 1 0, and when we have our enable equals to 1, we are able to load during the next clock. And we can see that when enable is 0 and everything is 0 0, we are able to retain the state of our circuit. And so that is it. So we can see that the circuit is actually working the way we expected it to. And as you can see that when we have our enable equals to 1 and everything else is 0, that is the load and the synchronous clear, then we can see that our clock is actually our counter, is actually incrementing. And when everything is 0 0, we can see that we are able to retain the current state of our circuit. So this is it. I hope you have been able to learn something from this particular design. See you in the next video. Thank you.